A matrix is in reduced row echelon form if it has ones along the main diagonal and zeros above and below those ones. So here we have a matrix that would be in reduced row echelon form. To the right of the augment bar, we would have constant values. I'm going to use A, B, and C just to represent those constants. But what makes this matrix in reduced row echelon form is that we have ones along the main diagonal, and the main diagonal runs from the top left to the bottom right. And then we have zeros above and below that main diagonal. So this would be a matrix in reduced row echelon form. When solving a system of equations using matrices, we want to algebraically manipulate our matrix until it is in reduced row echelon form, and we can also abbreviate that RREF. So the row operations that are allowed in order to get a matrix into reduced row echelon form is that we can interchange any two rows. We can replace a row by a non-zero multiple of that row. And the one that's a little bit tricky is that we can replace a row by the sum of that row and a non-zero multiple of another row. Let's take a look at a system of equations to unpack these first two row operations to see why those are allowed. If we convert the system of equations to a matrix, we would have the first row being 2, 1, and 4. Second row would be 1, negative 1, and 2. And then we have our vertical augment bar representing the equal sign. The first allowable row operation is that we can interchange any two rows. So we could write row 2 as row 1 and vice versa, which makes sense because that would be the equivalent of just writing the second equation first. So that is totally allowed. The second allowable row operation is that we can replace a row with a non-zero multiple of that row. Let's look at that from the perspective of the system of equations. We're allowed to multiply both sides of an equation by a constant value or a non-zero value. When we do that, we get a new equation that has the same collection of ordered pair solutions as the last equation. Essentially, it's the same line, which means that we could replace this second row with that non-zero multiple of the original second row, and this would not change the solution to the system. The third allowable row operation is that we could replace any row by the sum of that row plus a non-zero multiple of another row. And essentially what that means is that we could take these two rows and add them together. We would get 2x minus 2x, and these two terms just cancel out. Adding the y terms together, we would get 3y, and then adding the constants together, we would get 0 over here. So this new equation is the sum of these two equations, which means that it contains the criteria from the first two equations, and we could use that to replace either one of these rows because both of those criteria are contained in this new sum row. So we could replace either one of these rows with this equation, which would be 0 as the coefficient on x, 3 as the coefficient on y, and 0 as the constant value to the right of the equal sign. So let's look at an example where we start with the system of equations, we convert it to a matrix, and then we use allowable row operations to convert that matrix into reduced row echelon form, which will enable us to then solve that system. So the first thing we'll do is we'll convert it to a matrix. And this system of equations converted to a matrix is going to be row 1 will be 2, 1, and 4. We are augmenting with a vertical bar. Row 2 is 1, negative 1, and 2. Now we're going to use allowable row operations to get this matrix into reduced row echelon form, which as a reminder is going to have ones along the main diagonal, zeros above and below it, and then constants to the right of this augment bar. So when we do this, we want to go in a particular order. We want to try for the positive 1 in the top left position first, and we can do that just by interchanging these two rows. That will put this positive 1 into the top left position. So that's our first row operation. We now have 1, negative 1, 2 as the top row, and then 2, 1, 4 as the bottom row. We also need to designate what our row operations are with each step. We're going to use a capital R to represent the new row and a lowercase r to represent the old row. So what we'll say here is that new row 1 is basically just old row 2, and new row 2 is essentially just old row 1. So our first move was to get that 1 in the top left position. Our second move is to get the 0 in this position here. Since we're going to be changing the second row, we're not going to make any changes to the first row. we only change one row at the time. So new row 1 is going to be the same as old row 1 with no changes. So we'll say 1, -1, 2, no change to row 1. In order to get the new row 2 though, and again we want to have a 0 in that position, so our row operation is going to be built upon trying to get a 0 here. And in that previous iteration, what we see we can do is, if we multiply the first row by -2 and then add that to the second row, we would end up with a 0 in this position. So what we say here is that we're going to multiply old row 1 by -2 and then add that to old row 2. Let's rewrite this row operation down here to make it a little bit easier to calculate. So we're going to take -2 times old row 1 quantity, which is 1, and then add that to old row 2 quantity, which was 2. And that gives us the 0 in this position that we were after. So let's see what happens to these other two positions. Now we have to stick with this same row operation, and we're going to use the elements in this second column in order to calculate the value in the second column position. So this new row 2 element is going to be -2 times the element in old row 1, which is -1, plus the element in old row 2, which was +1. So our new row 2 element is going to be +2 plus 1, which is 3. Now we do it again to determine this third column element, and we're going to use the third column values from the previous iteration in order to calculate it. New row 2 is going to be -2 times old row 1, which in this case is 2, and then we'll add that to old row 2, which is 4. So this makes our new row 2 element -4 plus 4, which is 0. And so now we're going to move forward with the next iteration. So after we have the 1 in this position and the 2 in that position, the third element that we want to go after is the 1 in this position here. It's important that we go around in this order, and that's so that we can preserve the progress that we've already made with the previous elements. So in order to get a +1 in this position, all we need to do is to multiply this row by +1/3. But we're not supposed to write it like that. We need to officially declare our row operations. Since we're going to be changing row 2, again, we're not going to do anything to row 1. So new row 1 is just going to be a copy-paste of old row 1, which is 1, -1, and 2. But in order to get new row 2, what we'll do is we'll multiply old row 2 by +1/3. In order to get our first column element, we'll multiply the first column of the previous iteration by +1/3, and again we have 0. So we've preserved that element that we already worked to achieve. In order to get this next column element, we're going to multiply +3 by 1/3, which is going to be +1. To get our third column element, we multiply the third column element from the previous iteration by +1/3, and again we have 0 here. And the last thing that we need to do is to get the 0 in this top right position. And in order to get a 0 in this position here, all we really need to do is to add these two rows together, because 1 plus -1 is going to be 0. But we need to officially declare what row operations we're using. And if we're going after getting a 0 in this position, that means we're changing row 1. And when we change row 1, we do not change row 2 at all. So we copy-paste our row 2, which is 0, 1, and 0. And in order to get new row 1, we're going to take old row 1 and add it to old row 2. So to get the element in the first column position, we're going to use the first column of elements from the previous iteration. Row 1 plus row 2 is 1 plus 0, which is still 1. To get the element in the second column, we're going to use the elements in the second column from the previous iteration. We'll add row 1 to row 2 to get 0 in this position. To get our third column element, we'll use the elements in the third column from the previous iteration. We're going to add row 1 to row 2, so it's 2 plus 0, which is equal to 2. And that completes our matrix that is now in reduced row echelon form. Once we have our matrix in reduced row echelon form, this is when we want to convert back to the system of equations. Remember, the first column represents the coefficient on the x's, the second column represents the coefficient on the y's, and the constants to the right of the augment bar represent the numbers to the right of the equal sign in the system. So this first row is going to translate back to 1 is the coefficient on x, 0 is the coefficient on y, and to the right of the equal sign we just have 2. To translate the second row back to the equation, we have 0 as the coefficient on x, 1 is the coefficient on y, and 0 is the constant to the right of the equal sign. So this is the solution to the original system of equations, but we could also write this solution as an ordered pair, because remember, the solution to a system of linear equations is the ordered pair that is the intersection point between the two original lines. So we can represent our answer in either one of these ways.